All right, so for this last lesson, we're going to talk about triangle centers, and we're going to use constructions to find those. And as the title suggests, there's more than one. So kind of like if you're looking at this triangle, the idea is where is the center of that triangle? Well, we're going to look at 4 different centers found by 4 different lines that meet at a point called a point of concurrency, and that point of concurrency is the center. And the first triangle center we're going to look at is called a centroid. Now a centroid is the intersection of 3 medians. Okay, we haven't defined that yet, but a median simply goes from vertex to midpoint. Vertex to midpoint, vertex to midpoint, and that point of concurrency, which is a point where all 3 lines intersect, is called a centroid. Okay, so there's one type of center, it's called the centroid. Another center is called an orthocenter, and that's the point of concurrency. That's where 3 lines intersect. It's the point where 3 altitudes meet, so the height of the triangle. Every triangle has 3 heights depending on how it's oriented, so these 3 heights intersect at the orthocenter. Okay, you can see if it's a right triangle, the orthocenter is right on the triangle, and if it's an obtuse triangle, the orthocenter is outside. Okay, the center of the triangle is outside. That's an orthocenter. Okay, we'll talk more about that in a minute. The next kind of center is called the incenter. Okay, this is the center of the triangle where 3 angle bisectors meet. Okay, so each one of these, in this case ray, each ray is an angle bisector, and they always meet at a certain point called the incenter. And the last one is the circumcenter. The circumcenter is the intersection of all the perpendicular bisectors of the sides. Okay, so here we have a perpendicular bisector of segment BC, right? Perpendicular bisector of segment AC, and a perpendicular bisector of segment AB. They all meet at the circumcenter, and like the orthocenters, the circumcenter can be inside, it can be on, or it can be outside. Okay, so now let's take out the notes and we'll fill in some more specific information about each one. All right, so here we have the notes I gave you. These work by just folding the sides to the center. Right, so what we have now is that the centroid is the intersection of the medians, the orthocenter is the intersection of the altitudes, the incenter is the intersection of the angle bisectors, and the circumcenter is the intersection of the perpendicular bisectors. Okay, so we open this up, and what we have is on the left side, we have all 3 segments meeting at the center, and on the right side, we have a picture of just what the segment looks like by itself, so just one of them. Okay, so for this first one, we are going to talk about the centroid as being the intersection of the medians. So 3 medians intersect at the centroid. Okay, so you may be like, not sure what a median is. Well, here it is. A median is a straight line that joins the midpoint of a side to the opposite vertex. Okay, so over here is a single median going from midpoint to vertex. That's a median. And on the left side, we see a diagram of 3 medians intersecting at the centroid. So point G is the centroid. Now the centroid has a specific property in relationship to the segments of the median, and it divides each median into 2 segments, and the segment joining the centroid to the vertex is twice the distance of the segment joining the centroid to the opposite side. You might be wondering, what did he just say? What I said is, the segment going from vertex to centroid is twice the length of the segment going from centroid to side. So this is twice the length of this shorter piece. Okay, and that's true for all of them. This longer segment is twice the shorter segment. Okay, so that means that from the vertex, there's a 2-to-1 ratio, and the centroid also has a special property of being the center of gravity, meaning if you were to cut out this triangle, you could balance it right there. All right, so right now we're just looking at a triangle that's got 3 medians going from vertex to midpoint, vertex to midpoint, vertex to midpoint. And right here is the centroid. Okay, that's the center of gravity or the balance point. And the idea is no matter what kind of triangle you have, if it's a right triangle, if it's an obtuse triangle, if it's maybe an acute triangle, that centroid is always going to be inside. The center of gravity will always be in. All right, the next one is the orthocenter, and the orthocenter is where three altitudes meet. So three altitudes, another name for altitude is just the height of the triangle, intersect at the orthocenter. So here's one altitude. Every triangle has three, just like every triangle has three medians. Every triangle has three altitudes. Here's one. And here's a diagram that shows three altitudes meeting at the orthocenter. So H is the orthocenter. Now each altitude is a perpendicular line that goes from one vertex to the opposite side. Okay, or its extension. Sometimes the perpendicular is going to drop outside the triangle. Let me show you what I mean. If I want to draw a perpendicular line that goes down, it's going to have to be outside the triangle. Okay, and the orthocenter is inside if the triangle is acute. It's on if the triangle is right. And it's outside if the triangle is obtuse. Okay, so in this example, we're just looking at a triangle that's got three altitudes drawn. An altitude goes from a vertex to an opposite side at 90 degrees. Right, so here's the vertex going to the opposite side, vertex going to the opposite side, and this center is called the orthocenter. Now, right now we have an acute triangle and the orthocenter is inside. But if we increase to a right triangle, you can see that the orthocenter is now right on the triangle. It's at C. And if we go further and go to an obtuse triangle, we can see that the orthocenter is now outside the triangle. In fact, it's way below. So that orthocenter can be out, it can be on, or it can be in. All right, so now we're going to take a look at the incenter and its special properties. And we can say that the angle bisectors, or three angle bisectors, intersect at what's called the incenter of a triangle. Okay, the incenter is always inside the triangle. And what's kind of unique about the incenter is it's actually not the center of a triangle as much as it's the center of the inscribed circle in the triangle. Okay, so that's why we call it the incenter. It's the center of a circle, or it's the center of a triangle, but it's the center of the circle inside the triangle. Okay, so it is the center of the circle inscribed in the triangle. And you can see over here we have one angle bisector, and then all three of those meet at a point. In this case, we call it the incenter. And what's unique about the incenter is that if we can draw a circle, that means we have distances from the center that are all the same. So the distance to each side, and distance is always measured at 90 degrees, all three of these distances to the side of the triangle are the same. So the incenter is equidistant from each side, measured by a perpendicular line. Okay, so here we're just looking at the incenter, which is the point of concurrency, where three angle bisectors meet. And again, like the centroid, the incenter is always inside. And specifically, the incenter is actually the center of the inscribed circle that fits inside that triangle. Now, you don't see the radius of that circle. It's the distance from the incenter to the side at 90 degrees, and all those distances are the same. So this incenter is the same distance away from AC as it is from BC, as it is from AB. And since it's the same distance away, we can make a circle on the inside that goes around that incenter. Okay, so that's kind of its special properties. It's the incenter is the center of the inscribed circle, and the incenter is always inside. Okay, and this last center is called the circumcenter. And the circumcenter is formed by the intersection of three perpendicular bisectors. Okay, so here's one perpendicular bisector, here's two, and here's three. And then this center is called the circumcenter. Okay, so three perpendicular bisectors intersect at the circumcenter of a triangle. And one unique feature about the circumcenter is that it's the same distance from each vertex, or it's equidistant. Okay. Well, if this point is the same distance from each vertex, that means if we put our compass point at O and open it up to A1, well, then it's going to reach this point of A2 and this point of A3. So we can make a circumscribed circle. So the circumcenter is the center of the circumscribed circle. Okay, so this means that the circumcenter is the center of a circle circumscribed around the triangle. The circumcenter is inside if the triangle is acute. It's on, so that center of the triangle is on the triangle if the triangle is right. And it's outside if the triangle is obtuse. So for this last example, we're looking at perpendicular bisectors. So right now, this purple line is a perpendicular bisector of segment AC. This perpendicular line is a perpendicular bisector of BC, and this purple line is a perpendicular bisector of AB. And all three perpendicular bisectors meet at a point, so that's why we call it a point of concurrency, and that point is called the circumcenter. Now this one can also be outside, on, or inside. So the circumcenter can be outside. So right now, if you put your compass here and opened it up to measure out to B, that circle would touch all three vertices. And the same thing is true here. Put your compass here, it's the same distance. And notice, that makes sense, it's right at the midpoint. It's the same distance from B as it is from C, as it is from A. Okay, that's it. In class, we're going to do constructions of each one of these, and then we'll do a little practice with all their special properties.